Superconductors are really practical and have potential applications, for example, in nuclear spin tomographs, magnetic levitation trains, or nuclear fusion reactors. But superconductors are also very interesting for our electricity grid. This is because superconductor cables are a crucial key to the energy transition. In Munich, a lovely town in the south of Germany, a superconductor is currently being tested as a cable in the SuperLink project. The German government has invested more than 5 million euros in this project, and with this project, the world's first prototype of a high-voltage superconductor has now gone into operation. And it could soon be 15 kilometers long, making it the longest superconducting cable in the world. But how does the project work? Basically, the first thing to know is that normal conductors have an electrical resistance. This has to do with the interactions between the electrons and the crystal lattice of the material. A superconductor, on the other hand, is a material with an electric resistance of almost zero, at least at a certain temperature. However, one only speaks of a superconductor if the material fulfills 3 conditions. Let's start with condition number 1. The material must fall below a certain temperature limit to be superconductive. This temperature limit is also known as the critical temperature or transition temperature. It is so called because this loss of resistance occurs very abruptly. However, to achieve a resistance of almost zero, the superconductor must be extremely cold. How cold varies depending on the material used. However, the temperature is often just above absolute zero. Take mercury, for example. The critical temperature here is 4.2 Kelvin or minus 268.95 degrees Celsius. The Dutch physicist and Nobel Prize winner Heike Kamerlingh-Onnes discovered this phenomenon in 1911. However, there are now also superconductors that no longer need to be quite so cold. A distinct is therefore now made between low temperature superconductors and high temperature superconductors. Low temperature superconductors normally require critical temperatures of less than 20 Kelvin. That is approximately minus 253 degrees Celsius. For high temperature superconductors, on the other hand, a higher critical temperature of around 77 Kelvin or around minus 196 degrees Celsius is sufficient. That still sounds extremely cold, and of course it is, but in the field of application it actually makes a big difference because you simply don't have to cool them down that far. In practice, this means that instead of expensive helium, you can also use cheap nitrogen for cooling. In addition to the critical temperature, there are now 2 further conditions. And this is where we come to condition number 2. A superconductor must fulfill the Meissner Effect. In the Meissner Effect, a superconducting material always displaces a magnetic field from its inside and guides it around the outside. This turns the superconductor into a perfect diamagnet. Diamagnetism always occurs when a material weakens an external magnetic field. A superconductor does not simply weaken the magnetic field, but guides it around the outside. This also reduces the magnetic resistance in the superconductor to zero. And this brings us to condition number 3, namely electron-phonon coupling. And that brings us to the actual physics behind superconductors and the questions, what actually happens there? We already know that superconductors have no electrical resistance at extremely low temperatures. This means that the electrons move unhindered through the crystal lattice of the material. This is because any collision with the lattice would cause friction and therefore a loss of energy. But what happens instead is explained by the so-called BCS theory. Let's take a closer look at it. The starting point here is an electron. It now moves along the ions of the crystal lattice. This causes the electron to generate a lattice vibration, which is called a phonon. This oscillation causes the lattice to deform, forming a region with a positive charge density. This means that there are more positively charged ions than negatively charged ions. This positively charged region can now attract a second electron, and normally 2 electrons would repel each other. At low temperatures, however, the attraction is stronger than the repulsion, and this creates electron pairs which are known as Cooper pairs. The electrons in such Cooper pairs have opposite spins. As a result, they have a total spin of 0. Such particles are also called bosons, and these bosons can move through the lattice without resistance. To summarize, as long as it is cold enough, Cooper pairs form, and because all electrons in the superconductor are bound in Cooper pairs, there is also no resistance in superconductors. This phenomenon is actually extremely complicated. I had a course at university that spent almost half the semester just on this, but this was at least a brief summary of it, and it is enough to understand the concept of the superconductive cable. Now let's move on to practical applications, and specifically the use case, for example, electricity grids. And electricity grids in Germany are quite old. Many power cables in Germany are now more than 50 years old. They are therefore approaching their intended service life, just in time for the energy transition that is also happening here right now. Because of this, we will have to transport much larger quantities of electrical energy in the future. Because where we use fossil fuels today, electrification will continue in the future. For example, in transportation or heating systems. And for larger quantities of electricity, we also need better electricity conductors with a higher power density and less heat loss. The transmission capacity can still be significantly improved here by a factor of 5 to 10. High temperature superconductors in particular are far superior to conventional copper cables and have great potential. And that is why such a cable is now also being tested in Munich. The manager of the local project even says a superconductor cable can transmit 5 times as much electricity as a copper cable. And that's just one advantage. The increase in efficiency would mean that fewer power plants would be needed and fewer greenhouse gases would be released. The Federal Ministry for Economic Affairs and Climate Protection has extrapolated this for 15 major German cities. If superconductor cables could save even just 1% of urban connected load, then these 15 cities together would save around 880 gigawatt hours of electricity every year. That would be over 600,000 single-person households. And as I said, that's per year. And superconductors are also supposed to be space-saving. If you compare a superconductor with a conventional cable, the superconductor needs much less voltage to transport the same amount of electricity. And lower voltage ultimately also means a smaller transformer station. Here's another small comparison. A substation in regional transportation grid requires around 110 kilovolts. This makes it about the size of a school. However, a transformer station for a superconductor only needs 10 kilovolts. And therefore fits easily into a double garage. Also, such a superconductor should be super cheap. The project manager says compared to conventional cable systems, the installation cost would be 32% lower and the operation cost would also be 15% lower. That may sound a little bit unrealistic at first, and it made me hesitate. But you have to remember, in cities in particular, space and rights of way are often rare and above all expensive. Here, high temperature superconductors don't need massive cable installation or tunnels, just a narrow trench. Above all, this reduces the cost for civil engineering and service restoration. In cities, these alone often account for 70 to 80% of the total cost of the cable route. I have to say, I was actually very surprised by this during my research. The advantages of superconductors in power grids are therefore obvious. But the thing is, there's a catch here too. And without giving too much away, in Essen, an old coal town in West Germany and my hometown, there used to be a superconductor like this, but it has been shut down. I will tell you why they decided to do this and which challenges from Essen might also become a problem for Munich. But before that, we need to take another quick look at this project in Munich. The project manager here is from Stadtwerke München, which is the energy provider. They work together with the KIT, a research facility in Germany, and with NKT, a cable manufacturer, and 2 other companies. They are responsible for the superconductor. Together they have developed a superconductor cable that has to meet special requirements. On the one hand, it had to have the ultimate current carrying capacity. On the other hand, it had to have the ultimate current carrying capacity and be flexible. It should be mechanically very robust and offer safety mechanisms in the event of an overload. The project also aims to reduce the production cost for such a cable. The main focus is on the conductor. These currently account for around 2/3 of the cable cost, but they have already come a long way at around 50 euros per kiloamp meter. This is comparable to copper wire cables. Incidentally, the kiloamp meter is a unit for measurement used to describe the cost of electrical conductors. But what does the cable look like now? A superlink cable should consist of 3 high-temperature superconductor cable cores. These are brought together in a tube. Liquid nitrogen now flows in this tube. The nitrogen has 2 functions here. On the one hand, it is a cooling medium, and on the other hand, it serves as an insulator to prevent short circuits between the cable cores. These 3 wires are now in a pipe, and there's another tube around the pipe. This is mainly used for thermal insulation. There's also a vacuum between the 2 tubes, which also has an insulating effect. Superlink is not the first project to develop such an HTS cable. In Essen, for example, there was the Amper City cable project with 1 kilometer cable. It was the longest ATS cable ever implemented in 2014. In Munich, a 6-month test phase has now begun in October with a 150-meter long prototype. This is located in the main Menzing substation network. And if the test phase is successful, the superconductor will be even longer. Superlink is planning 15 kilometers. This would also make it by far the longest HTS cable to date with a planned output of 500 megawatts. However, superconductor cables this long also need efficient cooling, and that brings us to what is probably the biggest hurdle. And today, as always, we will be discussing them in the big problem. Before that, why don't you quickly leave a subscription and activate the bell? So, the big problem. First of all, we have to look at the Amper City project in Essen that was discontinued after 7 years. So, what happened there? The project was actually only planned for 4.5 years. 7 years sound pretty good at first. However, the superconductor cable was replaced by conventional cables. It was relatively difficult to find out why this was done. That's why we simply contacted West Energy for more detailed information. They were the last responsible grid operator at the time. And we asked them, why was the superconductor cable taken out of the grid again? West Energy actually told us that the superconductor was not cost effective and was therefore taken out of service. The main problem was the cost of cooling. However, the superconducting cable was more expensive than the conventional cables. We then searched a little further and got in touch with someone from the KIT, one of the research institutes. He told us Amper City was a first-of-a-kind development project and never claimed to be economically viable. So if we look at the success of the project, profitability is probably not the right indicator. The KIT manager also emphasized that Amper City had provided the project partners with valuable technical insights. And at this point, it has to be said that it is hardly surprising that a technology is generally always more expensive at the beginning of its development. And of course, cooling a superconductor is expensive. This can also be seen in the project in Munich. Cooling over a distance of 15 kilometers is of course a particular challenge. With a superconductor cable in Essen, it was easy to cool the 1 kilometer from one side. This would not be so easy with a 15-kilometer cable. In theory, you would probably have to build a station every 4 to 6 kilometers to recool the cable, and a modular cooling concept would probably have to be developed first. However, the Superlink project is also optimistic in this point. Comparisons and calculations have shown the electricity heat losses of conventional cables exceeds the cooling energy requirements of HTS cables, and the cables are supposed to be in the ground for a while. And there too, the calculations show a clear result. Over 40 years, HTS cables are significantly cheaper than copper cables with the same performance, especially when the prices for energy, CO2 certificates and civil engineering rises, and we have to assume that this will happen. An HTS cable will only become more economically in comparison when this happens. Even if such a cable is perhaps less economical in the short term, it is probably more economical in the long term. Oh, and by the way, you find all my sources in the video description, and the numbers down here, they indicate when which source is used. Okay, let's get to the conclusion. I think this whole idea is really cool, which is quite funny, and I'm really excited to see how it develops. One exciting aspect here, for example, is retrofitting. The project in Munich also wants to address this. How can we perhaps use the existing cable tubes, and can we develop a completely new compact cable design? And also, what is the solution to the cooling problem? It will be extremely exciting to see what path the project takes. As always, I will keep you up to date. Take a look on this video about a new very big Stirling engine. It's an amazing technology, and I say auf Wiedersehen, macht's gut, your Jacob.